Guys, this is Chapter 16, Section 2. We've already covered the first section, and the first section dealt with electric charge, and now we're going to move on and apply this, talking about electric forces. And the first thing we're going to look at is Coulomb's law. Two charges near one another exert a force on each other. This is called an electric force. And what are the types of charges we've talked about? Positive and negative. So if like charges get near each other, what happens? They repel. Opposite charges attract. So now we're introduced to Coulomb's law, and we've already looked at it, but now we're going to look at an equation that goes with this. It states that the electric force is proportional to the magnitude of each charge and inversely proportional to the square of the distance between them. Kc there is Coulomb's constant, and we will get to what that constant is. It is a value that you're going to need to memorize. Q1 and Q2, it tells you, are the charges, and I told you that the lowercase q is the symbol that we use to talk about charge. And then the distance between the two charges, they're using the symbol r, which looks a lot like radius, but that is the full distance that is between the two charges, and you square that. Coulomb's constant, we're going to look at it in a problem because we're going to go ahead and go through a sample problem. Do y'all have this written down? Okay, let's look at a sample problem then. Here's the problem that we're going to look at. The electron and proton of a hydrogen atom are separated on average by a distance of about 5.3 times 10 to the negative 11th meters. Find the magnitude of the electric force and the gravitational force that each particle exerts on the other. So let's talk about some of the information that we actually have. We've not looked at gravitational force yet. That was in a chapter that we skipped over, but I think once you see the equation, it's going to be pretty easy to move from there. So what was the equation that we looked at on the previous slide?
Electric force equals Coulomb constant times charge over distance squared.
Okay. So Kc, Q1, Q2 over R squared. Let me go and give you the value for Kc. Kc is equal to 8.99 times 10 to the 9th Newton times meter squared over coulombs squared. Kc equals 8.99 times 10 to the 9th Newton times meter squared over coulomb squared. 8.99 times 10 to the 9th Newton times meter squared over coulomb squared. That's our value for Kc. What's some other information that's given in this problem? Distance. What do you think we're going to do with that? Where at though? For R. It is for R. So R is equal to 5.3 times 10 to the negative 11th meters. Do you think we're going to have to change that? The units on it? No. It's in meters, and that is a unit that we've worked with. What about the Q? Do we have the values for Q? Q1 and Q2, what are Q1 and Q2 here? Of electron and proton. Do you know the charge of the electron and the proton? That's the unit. Did we not just go over that charge in the previous section when we went over? Thank you. 1.6, yeah. Right, 1.60 times 10 to the negative 19th. And I know when they work this out, they end up leaving off some of the 2 that's on there. So you go ahead and plug this in. You've got your Kc value. Q1 and Q2, that's the charge of the proton and electron, numerically exact same value. One's positive and one's negative, the 1.6 times 10 to the negative 19th coulombs. And then your R value, that's the distance between the two, plug that in as is. And make sure you square your R value. Once you get your answer, let me know what you've got. I'll go ahead and work this out while they're working on it.
Yes, that's awesome.
That's what you mean right there.
Hopefully you have yours set up basically about the same way that this is right now.
What about the negative?
Is it going to be important when we're talking about the electric force?
No.
Okay, I know we haven't talked a lot about that, but when you're talking about electric force and you're going to be comparing it to gravitational force, it's not going to matter.
No.
Not here. Who's got an answer? Anybody get an answer?
8.2 times 10 to the negative 8.
That's what I'm looking at. 8.2 times 10 to the negative 8th newtons.
You don't need a negative.
No. That original question also had one more part to it, and the part that it added to it was also find the gravitational force. And again, this was something we did not go over because that was a chapter that we skipped, but after you've seen the equation for electric force, this one's not so bad. Fg for gravitational force, and again, this is us working with very small particles at the time. You've got another constant. They're using a capital G for your gravitational constant, and I'll give you what that value is. And then it's going to take the mass of the two particles. In this case, we're taking the mass of the electron and mass of the proton and dividing it by the distance between the two. Gravitational constant is 6.673 times 10 to the negative 11th. Newton times meter squared. Instead of coulomb squared, instead of charge, we're dealing with mass, so it's going to be kilograms squared. And then you've got to take the mass of your electron and mass of your proton. Seems like this was, if not the previous section, it would have been in the chapter that we skipped, but I can give you those.
Wait, is it always going to be 6.673?
Yeah, it's a constant. It's a constant. Mass of an electron. Is the electron or proton more massive?
Proton.
The proton. So mass of the electron, 9.1 times 10 to the negative 31 kilograms. Mass of the proton is, we'll say 1.7, and I'm cutting off a bunch of decimal places here, times 10 to the negative 27th kilograms. So 1.7 times 10 to the negative 27th kilograms. Divide all of that by our R value, or in this case the distance is 5.3 times 10 to the negative 11th meters, and make sure you square it. Let me know what you get as an answer. The answer that you should have gotten for the force of gravity was 3.6 times 10 to the negative 47th newtons. Okay? So just showing you gravitational force was much bigger or smaller than electric force?
Smaller.
Much smaller, so it's going to be negligible compared to the electric force between the two particles. Resultant force. Again, you've seen the term resultant force before. On a charge, it's the vector sum of the individual forces on that charge. So when you add your forces, this is called the principle of superposition. And when a body is in equilibrium, the net external force acting on that body is 0. we're going to look at an example. The video is going to show you how they solve for, you've got basically three forces or three charges, two of them acting on a third. How do you break it into the components and all of that other good stuff. And then we're actually going to go through and solve. Okay? So we're going to watch the video, and then the rest of the time we're going to look at actually solving for this.
Like any other vector quantity, electric forces have both magnitude and direction. Consider a positive charge Q3 in the vicinity of a positive charge Q1 and a negative charge Q2. Suppose you want to find the net force acting on Q3. First, identify the individual forces acting on Q3. Because Q3 and Q1 are both positive charges, they repel each other. The direction of this force lies on the same line that joins Q1 and Q3. Q3 and Q2 have opposite charges, so they attract each other. The direction of this force lies on the same line that joins Q1 and Q3. The resultant force on Q3 is the vector sum of these two forces. The superposition principle allows you to calculate the electric force of several charges acting on the charge Q1 as the vector sum of forces of each of the charges acting on Q1 independently.
Okay, so what we're going to look at is we're going to know the actual charges of Q1, Q2, Q3, and then we're going to figure out, well, what is the resultant force if you have all three of those charges acting on each other? So here's the problem. Make sure you write down the charges for Q1, Q2, and Q3. And then we're going to work with this superposition principle, and we're going to figure out what the magnitude of the total force is acting as far as a resultant force goes. Okay, so looking at the three charges that were given, you had Q1 and Q2 and Q3. Q1 was positive or negative? What about Q2 and Q3? So I want to make sure first off that you know how they came up with the forces they were looking at based off each one. Q1 and Q3 will do what? They'll repel. So looking, you've got a force moving this way. Q2 and Q3 will attract, so you have another force that's moving this way. It gives you the distances. Did it give you the distances?
Yes.
Okay. This distance was 5 meters, 3 meters, and 4 meters. So are we dealing with the right triangle? Yes, we are. So moving on. First, we want to determine the direction of the forces by analyzing the charges, which we have already done. Now we've got to calculate the magnitude of the force, and we're going to use Coulomb's law to do that. What was the equation for Coulomb's law?
F electric equals Kc times Q1 and Q2 over R squared.
Okay, Kc times Q1, Q2 over R squared. Let's start with 1 and 3. I think they called it 3, 1. Okay, the interaction between charge 1 and charge 3. What are you going to plug in for K?
8.99 times 10 to the 9th.
8.99 times 10 to the 9th. I'm going to leave off units for now. That's Newton times meter squared over Coulomb squared. What are you going to plug in for Q1?
6.00 times 10 to the
I think they're actually, because I have it labeled 3-1, it does not matter if you want to start with the 6.00. I'm just going with the subscripted label we've got, so we would actually start with Q3 first, which is the 5 times 10 to the negative 9th. And what's the charge for Q1?
6 times 10 to the negative 9.
Okay. Stop it. And the distance between the two?
5 squared.
5 meters, so make sure you square that. Anybody have an answer for that force yet? Once you get an answer, let me know. As far as rounding goes, I'm going to go ahead. That was close. Not sure where the rounding difference is, but 1.8 times 10 to the negative 8th newtons. And now we need to do the same thing with the other two charges. How do 3 and 2 correspond? I'm not going to write down the equation again, but you've got Kc, which is still 8.99 times 10 to the 9th. You've got your two different charges, 3 and 2. So charge 3 was 5 times 10 to the negative 9th. Q2 is negative 2 times 10 to the negative 9th. I'm just writing it down as 2 times 10 to the negative 9th. And then the distance between those two is 4 meters. So square the 4. When you get an answer, let me know what you got. (5.6) times 10 to the negative 9th newtons. The negative value would show you that you're dealing with two charges that attract. So you can still leave the negative off. It is showing you more of a direction in what's going on between the two charges because the two charges do attract there. Now when we're looking at that, here's what we've actually found. F31, again, you originally had this, this, and this. F31 was moving in this direction, right? F32, which direction would you say it was going? Okay, it was moving in that direction. So if you go back to when we were doing our laws and how do you write out vectors, remember tip to tail method? I'll refresh your memory. So I'm going to erase that last one, and you actually start at the tip of one and move here. So whatever you see in pink goes with the F31, whatever you see in green goes with the F32. So now we're looking for our resultant, right? Okay? So the resultant is going to move in that direction. That's our resultant. How do you think we're going to move? We have an answer for F31. Okay? We know that this force is 1.08 times 10 to the negative 8th. We know that our other force is 5.62 times 10 to the negative 9th. How are we going to find that resultant force? What are we going to have to do? Because that's not at 90 degrees any longer.
Break them into X and Y. Well, it gave us that.
Yep.
It gave us
Which angle did they give us? Do you remember?
37.
Do you remember where it was at?
It was like
It was
up
like-
above 3. We continued off the 3
It was,
Okay. I'm going to write it in there. That angle right there. Theta is 37 degrees. But we're still not dealing with the 90-degree angle, right? We do have one angle, but we're not dealing with a 90-degree angle.
No. So we gotta do components.
Components. So if I'm looking here, let's see here. For the first one, we would look at f of x being equal to, I don't have my stuff drawn on here anymore. I don't want to go back and do it, but you've got the force of 3-1. Which we already saw for that, right? Times cosine 37. Plug in f of 3-1, which is up there in the pink, times cosine 37, and what do you get for an answer?
8.3 times 10 to the negative 9.
Close. 8.63.
Yep.
Okay, times 10 to the negative 9th newtons. Okay. What does cosine mean? Adjacent over hypotenuse, right? So what you actually see there in yellow is what we've tried to solve for. Okay, what you see there in yellow is what we've tried to solve for. Let's go to f of y. That is where we're dealing with 3-2. No, we're still dealing with 3-1. 3-1, and this time it's going to be sine of theta, so sine of 37 degrees. And what do you get?
6.5 times 10 to the
6.5 times 10 to the negative 9th. So that right there is us breaking up all of our vector that you see there in pink. This one right here, we've broken it up into its x and y components. Okay? So x and y components. That's what you see there in pink. What about the one in green?
Oh,
Is there going to be an x and y component for what you see in green?
it's just X.
It's just going to be x. So I'm going to move over to another slide.
Okay.
Again, you should have all that information sitting in front of you, but now if we're looking at force 3-2, all of this is in the x direction. Positive x or negative x? Look at the way the direction or the arrow was pointed. Okay, left, or it's going to be in the negative direction. So 5.62 times 10 to the negative 9th newtons. 5.62 times 10 to the negative 9th newtons. So they had it negative up there earlier. Again, it's going to show again here, but it's showing you direction. And f of y for this one is 0 because there's nothing in the y direction. Now, how are you going to find your x total and y total? Add them up. Add them up. So fx total, if I'm looking at it, you're adding the 8.63 and the 5.62. Both of those are to the negative 9th, and you should get 3.01 times 10 to the negative 9th. And then if you look at your Fy total, we only had one vector to go there, and that is what?
6.5 times 10.
Yep. 6.5 times 10 to the negative 9th newtons. Now, if we look at what we've got, and I'm going back and looking at this right here, what I see there as far as our purple vector, we have the x and y component, right? So now we got to find the hypotenuse. We have the x and y, got to find the hypotenuse. How do you find the hypotenuse?
What's that called? Pythagorean theorem.
Pythagorean theorem. So, F3 total. We're going to take the square root of all of it, but it's your Fx total squared plus your Fy total squared. Plug in your numbers, and you should get 7.16 times 10 to the negative 9th newtons. So like I said, we've just worked through this problem. You've got everything in the PowerPoint here. They're going to show you the details of how they set up everything. So you can look at the positives, negatives. There's all of the math, and it shows you how to find your components, the math that goes with it, and then your final answer. They also find theta for you there. Says, again, if we're trying to find direction, we've got a new angle that we're working with. And they do show you the angle there. It's Fy over Fx. They're using the tangent function, and they find that your new angle is 65.2 degrees. 65.2 degrees. So we weren't working with a 90-degree angle. Make sure you find angle 2. One other thing that's in this section is talking about field forces, and it says Coulomb's law is a field force. It's a force that's exerted by one object on another, even though there's no physical contact between the two objects. Even though there is no contact between the two objects. Have we talked about field forces before?
Gravity.
Okay, gravity being one of them. Let's see, when we have our next lesson on section 3, we will talk more about electric fields. We'll talk more about them. But I am going to work out one more problem for you. So resultant force, put them equal to each other, KC's end up canceling. What else ends up canceling? Q3 ends up canceling. Do we know what Q1 is?
Yes.
Yes. So you can actually plug in a value for Q1. I'm just going to write it here for a second. Q2, we know what it is. And then what have we put in place instead of R31? What is R31?
R31, 2 meters minus D.
2 meters minus D squared. And R32 is whatever D is squared. So now it's a math problem at this point. Can you see where you would plug in your numbers and you're solving for D? I'm going to go and give you an answer because of time, but it is algebra at this point, people. Plug in your numbers and you solve. D is 0.77 meters. D is 0.77 meters.
We use microcoulombs.
In this case right here, because of what we're looking for and you don't need QC or KC, you could use it as microcoulombs. It'll work out the same way either way. Who's got a question right now? Zach. Hey, y'all sit down. Sit down. What's your question?
Why does KC drop out?
It appears on both sides of the equation, so when you bring one over, it's going to cancel with the other. The same with Q3.